Okay, in this example, we're told that we have a cylindrical log with a radius r, length L, rests against the top of a dam right here. Water is level with the top of the log, so it's right at the top there, and the center of the log is level with the top of the dam, so that's in line there. And we can assume that the contact point with the dam is frictionless, so here the only force we'll have is a normal force acting to the left. And what we're asked to do is find expressions for the mass of the log, and the contact force between the log and the dam, so the force right here. And we're asked to express our answers in terms of a subset of these parameters. So let's first of all find the mass of the log, and we can do that by performing a force balance in the vertical direction. So let's put a coordinate system here. We'll say that y is pointing downward. We'll have x pointing off to the right-hand side, and we'll sum forces in the vertical direction, set it equal to 0. So acting downward, we have the weight of the log, so that'll be m times g. Okay, so m is the mass of the log. That's what we're trying to find. So that's acting in the positive y direction. Then acting in the negative, or at least countering that weight, will be the pressure force acting on the surface of the log. So what I'm going to do is I'm going to put a theta angle here out to where the radius is. So we're going to call that angle theta. And I'm going to draw a little bit of area acting on that. That area, dA, just the magnitude of it will be r times d theta times the distance in and out of the page, which is L. So that's just that little bit of area there. And the pressure force, just bear with me for a moment here, the pressure force, assuming that it was in water here, I know that this part of the log is not yet in the water, but when theta gets to be larger than pi over 2, it will be. I'm just going to pretend for a moment that it's there. That little bit of pressure force, here's the angle theta, and we'll have that little bit of pressure force, dFp, that will act on it there. And by the way, just from the geometry, here's the top of the log, and here's where that point is. So the top of the log, this distance out to the very top will be r, and then this distance here will be r sine theta. So the difference will be r minus r sine theta. Okay, so that'll be the depth from the free surface. Okay, so then the pressure force that will balance that weight, let me just write it here as Fp sub y. Okay, and then to find what the Fp sub y is, that's going to be the integral of all these little bits of pressure force. We're going to integrate them as theta goes from pi over 2 because that's where the water first starts to touch it, when theta is pi over 2 right there, all the way around until we reach theta equals 2 pi. Okay, so we're only going to really start counting the pressure forces once we hit this part, when it's pi over 2, and then it'll continue until we reach 2 pi. So let's go ahead and substitute in there. So go from pi over 2 to 2 pi. The pressure force will be the pressure times the area. Okay, and I just need to make sure I'm getting the right sign on this. I'll work out the signs when I get it all figured out once I substitute everything in. One of the other things I have to be careful of is I just want the vertical component, right? Just the vertical component of the force, the p sub dFp comma y, just the vertical component. So I really want to just take the sine of that force. So I'll throw in a sine theta there. That gives me the vertical component. And you'll see here that the way I've drawn it here, that this vertical component is in the positive y direction. Let me just draw that in there. So you'll see the vertical component acts downward this way. That little direction is the same as the y direction. So that's why this is positive. Okay, so let me go ahead and substitute in for the pressure. The pressure will be, oops, change the color. Here's our integral again. The pressure will be the density times gravity times the depth from the free surface, right? Remember, it's depth from the free surface. Well, I just said a moment ago that the depth from the free surface of this little area will be r minus r sine theta. Okay, so that's my pressure, and then my area I said was r d theta times L. That we said up here, that's just that little bit of area there. And then we have the sine theta that we have to put back in. So that's my pressure force in the y direction. Well, we can go ahead and simplify that. Let me pull out some constants. The rho, the g, there'll be an r squared and an L, all come outside the integral. And then what we're left with will be a 1 minus sine theta times a sine theta d theta. I believe I have that all correct there. And then we can integrate that expression. And I won't go through the details of the integration. If you want to see the details of it, you can look at the written out solution, which I've posted on the web, or you can I'm sure you can figure out the integral of this. This will just be the integral of a sine theta when I multiply through there minus a sine squared theta. So you can figure those out. But I'm not gonna work that out here just for the sake of time. But once you work out all the integrals, the pressure force in the y direction will end up being minus 1 plus 3 pi over 4 times rho g r squared times L. All right, so that's the pressure force in the y direction. Notice that it's negative, meaning that you get a net upward pressure force, which makes sense because it's going to have to balance the weight. So in the end, the mass times gravity will equal minus f p sub y here. So the mass, you can divide through by the gravity terms, and so the mass will be 1 plus 3 pi over 4 times rho r squared L. So that's how you can find the mass of the log. Essentially, all we did was just a vertical force balance, and then we found the vertical force due to the water pressure by doing our integration approach. We looked at a small little area, found the vertical component of that. We said what that area was, just r d theta times L. The pressure force would be the pressure times that little bit of area. We wanted the vertical component, so we take the sine theta of that, so that gives us that little vertical bit. The pressure was just density times gravity times the depth from the free surface. The depth from the free surface was this quantity over here. It's just, we have to go up a distance r from the center here, and then drop down a distance to this point. This point from the center was an r sine theta, so this depth from the free surface is r minus r sine theta, so that's where that comes from. And then to solve that integral is just math. That's ultimately what we get when all is said and done. So that's one way to solve this problem. There's another way there are actually a couple of different ways we can solve it. Let me do a different approach. Let me go back up to the picture. I'm going to erase some of the things that we've drawn here. Okay, so now another approach we could take would be, let's just balance forces on this kind of cubical, or at least square element that we have there. So I'm going to do a vertical force balance on that. So the vertical force balance will still have the weight of the log, but now we also have the weight of the water within that cube. So we have to make sure we have that weight, and that's all going to be balanced by a vertical pressure force acting down at that depth. That pressure at that depth will be the density times gravity times 2r. 2r because it's 1 radius and 2 radius. So 2 radii below the free surface to get down to the bottom here. So that's the gauge pressure acting at the bottom. And of course, to get the pressure force acting upward there, we'd take that pressure times the area that it's acting over. The area that it's acting over would be another 2r. That gives me the width this way. And then the depth in and out of the page would be L. So that would be the vertical force. So let's write that down. So this is approach number 2. So summing the forces in the y direction, set it equal to 0. Acting downward, we have the weight of the log, plus we have the weight of the water. Okay, so we'll have to figure that out in just a moment. And then we have acting upward is the pressure, which we said was rho g times 2r, times the area over which that pressure acts, which will be 2r times L. So that's the pressure force acting upward. Okay. Let's now figure out the mass of the water, right? So we need to figure out what this term is. So if we go up here for a second, you'll see that the volume of the water here is just going to be the volume of this square minus the volume of the circle, and then we only take this part we don't have to include. Right? So it's like taking the volume of the square minus the volume of the circle, and we only need to take into account 3/4 of the volume, because this little segment up here, there's no water there. Okay? So the mass of the water will be the volume of so it'll be the density of water. I'll just leave it as rho. Density of the water times the volume of the water. So that'll be the density of the water, and the volume of the water will be the volume of that cube. So it'll be 2r on each side, so we square that, times L. So that's the volume of this kind of whole cube here, and then the distance L is in and out of the page, and then we subtract out the volume of the cylindrical log, which will be pi r squared times L, and then we only need to take 3/4 of what's left over, because again, one of the quadrants is not filled with water, it's just air. So let me put that right up here, 3/4 of that. All right, so we can take that expression and substitute it in right up in here. Okay, I'm not going to work out the algebra, but trust me, you can plug that in and solve it. And then when you simplify down, you're going to get the exact same result as what we had previously. I won't go through all the algebra because I don't think that part's necessary. So this is the second approach we could have taken. So here, all we did in the second approach is we just took a kind of a system that looks like a cube, and we balanced forces. We took the weight of the log, the weight of the water, which was the volume of the water. When we calculate that weight, is just the volume of this cube minus the volume of the log, and then we only took 3/4 of it, because this part is just air. So we took those two weights and we balanced it by the pressure force acting on the bottom. With the pressure force down there, the pressure was rho g times 2r, because that's the depth from the free surface, multiplied by 2r times L, because that's the area over which that pressure is acting. So that's what this whole expression is. And you'll get the same result as before. Now the very last approach that we can take, we'll call this our third approach, will be a buoyant force kind of approach. Okay, so in this one, let me erase all that again. So in this approach, we're going to have the weight of the log acting downward, and that's going to be balanced by the buoyant force, which will be acting upward. The buoyant force acting upward, and by the way, that buoyant force will be acting at the center of the displaced fluid. But that buoyant force acting upward, it's the weight of the displaced water, right? The weight of the displaced water, as far as the water is concerned, the water that's been displaced is actually, let me highlight it, it's going to be the cylindrical log volume that's been displaced, but it also includes this part here that's been displaced, because normally the water would want to continue out, right, to that point. So the water that we've displaced is actually all of that yellow stuff. So it actually accounts for a little bit extra beyond the volume of the log. So let's write this down. So the buoyant force oops, let's rewrite that. So the buoyant force will equal the mass of the log times gravity, so it's just balancing the weight of the log, where the buoyant force will be the density of the water times gravity times the volume displaced, and the volume displaced of the water will be it'll be this. Go back up to the picture here. It'll be, let me just redraw this kind of square here. Let me highlight it in a different color. What I'm going to do to get the volume displaced is I'm going to take 3/4 of the cylinder and then add to it that little cube. Okay, so it'll be, the volume displaced will be 3/4 of the cylinder, which will be pi r squared times L. So it's going to be 3/4 of that. That's all the yellow bit that I highlighted up here. It's all the yellow. And then we're going to add in that little square, which will have a volume of r squared times L. Okay, so that's the buoyant force on the left-hand side. This is the weight of the displaced water, where the volume that's been displaced is this yellow bit plus that square bit. Because even though this is air, it's not part of the cylinder, but it's still been displaced. It's like we've pushed that amount of extra water out of the way and just filled it with air. And if you simplify this, you're going to get the same result as what we had before. You'll see the gravities cancel out, and what we're left with is rho r squared times 3 pi over 4 plus 1, whole thing times an L, which should be the same. Yeah, it's the same result we had up here. Okay, so there were 3 different ways that we could find the mass of the log. One was just doing the integration approach, found the pressure and integrated, we got that expression. The second way to do it was to just use a clever choice. I guess I erased it. We used a clever choice of a sort of a system, and we balanced the weight of both the log and the water with just the pressure force acting over the bottom of sort of a cubical shape. And then the third approach is we used a balance between the buoyant force and the weight that of the log itself. Okay, so anyway, that's the mass of the log. The next thing that we needed to do in this problem was to find the horizontal force acting on the wall. Right, so if we go back up to the problem statement, it's asking for the contact force between the log and the dam. So that force, let me just draw it here in some color here. It's going to be this force right here. So we're trying to find the force that the wall exerts on the log. And it's only in the horizontal direction because we said that it's frictionless, so we don't have to worry about that. Okay, so the way we can find that is we could go through the same approach that we did right here, but do it in the horizontal direction. So let's write that out. So here we're summing forces in the x direction, setting equal to 0. We'll have minus FW. Let me go back up to the picture. Sorry, I'm scrolling back and forth, but FW is pointed in the minus x direction. And then we'll have the pressure force in the x direction. Now, to find the pressure force in the x direction, let me redraw the picture of that log. Remember that we said our little area is right here. Here's a little bit of pressure force. That angle is theta. The area of that was r d theta times L, distance in and out of the page. That's our angle theta. And our little bit of pressure force in the x direction will be the pressure times the area times, this will be a cosine theta. And actually the way I've drawn it here, this should actually be negative, right? Because it's the x direction is this way. And then the pressure, recall, we said if this distance is r, then the depth from the free surface here we said was r minus r sine theta. And that'll help us with our pressure force. So the pressure force in the x direction will be the integral as theta goes from pi over 2 to 2 pi of the pressure, which will be minus rho g r minus r sine theta. So that's a pressure times the area, which will be r d theta times L times the cosine of theta. Okay, so this rho g r minus r sine theta is the pressure. It's just the density times gravity times the depth from the free surface. R d theta L is the little bit of area, that little bit. And the cosine theta gives us the horizontal component of that pressure force, just gives us the horizontal. And then there's a minus there because it's actually pointing in the negative x direction. And we're going to integrate that as theta goes from pi over 2, which was just kind of the part where the water touches it, all the way around to 2 pi. So we can solve for that. And again, I'm not going to go through the math of it, but when you go through it all, you'll get that the pressure force at the wall comes out to be 1/2 rho g r squared times L when you substitute everything in and solve. Okay, so that's the wall force. And now there's another way we could get that, and the other way we can do it is if we, let me redraw the log. Here's the, redraw the free surface of the water. Here's where the wall is. Let me draw the horizontal pressure force on the projected area. So what I mean by that, we've seen this in previous examples, is this will be the pressure force in the horizontal direction on the projected area looking in from the left-hand side, right, where this distance is 2r. And we know that that pressure force will be a 1/2 rho g 2r squared times L. We've done that kind of calculation many times before. Right, so that's the pressure force acting from the left-hand side, but you also have to remember there's actually a pressure force acting on this projected area from the right-hand side. There's still water over on this side. So that pressure force will look like this. It doesn't start at 0. Notice here, it doesn't start at 0, and the reason for that is because this is not a free surface here. It's the water here is at a depth r from the free surface. So it starts off at the pressure there will be a rho g times r, and the pressure down here at the bottom will be a rho g times 2r. Right down here it's rho g 2r as well. Okay, so you have to just be careful of that. So we have a pressure force acting on the right-hand side as well that's pushing back to the other side. So you have to be careful. But if you look at this for a moment, actually I'm gonna erase this over here for just to simplify. But if you look at this, you'll see, let me draw a horizontal line right through the center. This pressure force over here, let me highlight it in yellow. This pressure force on this side exactly balances that pressure force on that side. They're exactly the same. So the only bit of pressure force that we have acting horizontally is just this part right up in here. Let me highlight it in a light green. Is that little bit in light green? That's the only little bit that we have left. And that pressure force at the wall will be a 1/2 rho g r squared times L, because this distance is just r. Hopefully that makes sense to you. And you'll notice, by the way, that that is the exact same result that we have up here. So again, just to reiterate, what we're using here in this part of solving the problem this way is we're using projected areas. Now we've done this in some other example problems. So the projected area that the fluid sees kind of on the left side of the cylinder, that projected area is this whole 2r distance. And so the full pressure force acting on the left-hand side will be a 1/2 rho g 2r squared times L. But then you have to remember there's a pressure force that's acting on the right-hand side, and that's just going from the center of the cylinder down to the bottom, keeping in mind that this is not a free surface here, but this is, at this point, the pressure is rho gr. It's still below the distance r below the free surface. So we have this kind of pressure profile on the right-hand side, but you'll see that this part of the pressure profile on the left and this part on the right exactly balance one another, because they both start at the same pressure and they end at the same pressure, and they're both kind of linear profiles. So the only part that's unbalanced is this green bit. The depth from the free surface there is r, so the horizontal projected pressure force is a 1/2 rho g r squared times L, which is exactly the same result you'd get from the integration approach. So different ways we can solve this problem. And I won't recap everything. You can go back and look through the video if you want to kind of refresh your memory on how we did it all. But with these hydrostatic pressure force problems, we can use sometimes different methods to help us solve the problem. Some are a little easier than the other. I will say that the integration approach works all the time. It can be more complex mathematically, and if you're uncomfortable with that, you can take a different approach, but I kind of like the integration approach because it always works. All right, we'll go ahead and end the example there.